In this lesson, we'll continue our study of cyclic groups. To get us started, recall that R is the set of real numbers, and that's a group under addition, but not under multiplication. Here are a couple of tasks to get warmed up. So our first question, let R star contain the real numbers that have multiplicative inverses. And please describe the elements in R star. And as a reminder, R star is a group under multiplication. The second question, will let H be the smallest subgroup of R star that contains the number 3. And so see if you can describe the elements in H, the smallest subgroup of R star that contains 3. So please pause the video and work on these couple of problems, and we'll go over them shortly. So let's jump right to question B. Question A was asking the elements of R star. Those are real numbers that have multiplicative inverses, and those are all non-zero real numbers. And once again, R star is a group under multiplication. Now we'll let H be the smallest subgroup of R star that contains the number 3. And so let's see if we can write down the elements in H. Well, we got 3 in there already. Now, it is a subgroup of R star, and R star is a group under multiplication, so it must contain the multiplicative identity, namely 1. All right, what about closure? Well, 1 times 3 is 3, that's in there, but 3 times 3 should also be in there as well. So 9 should also be in there, and then 3 times 9, 27, and then 3 times 27, 81, and all these powers of 3 must be in this set if H were to be a subgroup. What else? Well, the inverses. So if 3 is in H, then its multiplicative inverse, 1/3, should also be in there. And likewise, 1/9, 1/27, 1/81, and so on, going in the other direction as well. And to summarize, we are left with all the powers of 3, including 3 to the 0, which is the multiplicative identity 1. We have all the positive powers of 3, and their multiplicative inverses, namely the negative powers of 3. And that, if H were to be a subgroup of R star, at the minimum, those elements have to be in there if we're starting off with the element 3. Now we can write this set a little more succinctly in the following form. This is a set containing elements of the form 3 to the k, where k is an integer. And we do need here both positive and negative powers of 3. The negative powers of 3 are needed because these are the multiplicative inverses of the positive powers of 3. And here is a new notation that we introduced last time. Bracket 3 refers to all integer powers of 3. And here we do need both positive and negative powers of 3. Let's review a notation from the previous lesson. We fixed an element little g of a multiplicative group capital G. We'll talk about the additive notation later in the lesson, but for now, let's assume that the operation of the group is multiplication. Then we define bracket G to be the set of all integer powers of our fixed element G. In other words, bracket G contains elements of the form g to the k, where k is an integer. So more explicitly, it contains all the positive integer powers of g, all the negative integer powers, as well as g to the 0, which is the identity element. So we just saw an example of this where our fixed element, the special element, was 3. Our original group was r star. And bracket 3 contains all of the integer powers of 3. That's the positive powers of 3, the negative powers of 3, as well as 3 to the 0, which is the multiplicative identity element 1. And last time, in the previous lesson, we proved the following theorem, namely bracket G is a subgroup of our original group G. And this theorem, although we're talking about all of this in the multiplicative setting, it does also, the same theorem holds even when the operation is addition. But again, later in today's lesson, we'll dig more into what all of this means when our operation is addition instead of multiplication. Now, using this notation bracket G, we can update our definition of a cyclic group. So here's our old definition. We said that a group G is cyclic if it has a generator. So that was our old definition. A group G is cyclic if it has a generator. So for instance, we said that U5, a multiplicative group containing 1 through 4, is cyclic because it has a generator, namely 3. 3 is a generator. How do we know? Well, if we take powers of 3, 3 to the first, 3 squared, 3 to the third, 3 to the fourth, this is all mod 5. Then we get all of U5 back. That makes 3 a generator of U5, and therefore U5 is cyclic. Now here's our new definition of a cyclic group. We say that a group G is cyclic if there exists an element inside it such that the group is equal to bracket G. So for example, 3 in U5 satisfies the condition that our group U5 is equal to bracket G, or bracket 3. Now why is that true? Because bracket 3 refers to the set of all powers of 3. And if we have all powers of 3, we have 1, 2, 3, and 4, which is the entire set U5. And so we say that group G is cyclic if there exists a single element little g such that the whole group is equal to bracket G. Now, that's another way of saying that our little g is a generator of our group G. And so it does boil down to the existence of a generator. So conceptually, this is no different from our old definition of a cyclic group. Now we're just using this new notation of bracket G. And so, as our example, we say that U5 is cyclic because U5 is equal to bracket 3, where 3 is the generator of U5. Now please pause the video and work on day 14 classwork. And afterwards, we'll go over some of the questions and concepts. In today's classwork, we looked at examples of cyclic groups whose operation is addition. So Z12, for instance, is generated by the element 1 because if we take all the sums of 1, 1 plus 1, 1 plus 1 plus 1, and so on, final element 1 plus itself 12 times, that gives us the additive identity element 0. That way we get all the elements of Z12. Now, repeated addition, such as 1 plus 1 plus 1, can be written more succinctly as 3 times 1. And so that's why we can represent this set as follows. It's the elements of the form k times 1. 1 here is a generator, where k runs over all the integers. And therefore, bracket 1, when our operation is addition, refers to the set of all possible sums of 1. Now we could ask the question, does Z12 have any other generator besides 1? And in the classwork, we saw that, in fact, yes, Z12 could also be generated by 5, by taking all the sums of 5, or 7, or 11. So Z12 has 4 generators, 1, 5, 7, and 11. Here's another additive example we saw. The integers, also generated by the element 1. And here we do need both positive and negative sums of 1, because if we take just the positive sums of 1, we get only the positive integers, and we don't get their additive inverses. And so when we say bracket 1, again, we're talking about the elements of the form k times 1. Remember, multiplication can be thought of as repeated addition, where k runs over all the integers, both positive and negative. And therefore, we can say that z is also generated by negative 1, because if we take all the positive and negative sums of negative 1, we get all the integers back as well. And so z has 2 generators, 1 and negative 1. And I'll leave it up to you to convince yourself that those are the only generators of z. Let's switch gears and work with a multiplicative example. Now we've seen that U13 is cyclic with a generator 2. And so if we take all the powers of 2, 2 to the first, 2 squared, 2 to the third, all the way to 2 to the 11th, and then 2 to the 12th, which we'll also call 2 to the 0, is equal to 1. And therefore, we can say that element 2 has order 12. Now underneath it, I've listed what these powers of 2 compute to. So for instance, 2 to the 5th, if we compute that, mod 13 is equal to 6. But we've also seen that working with these powers of 2, given that 2 is a generator of U13, can be a very helpful thing. And to illustrate that, I will highlight this correspondence that we've seen between the additive group Z12 and the multiplicative group U13, where an element k in Z12 corresponds to 2 to the k in U13. So for instance, 5 in Z12 would correspond with 2 to the 5 in U13. Now, how can we use this correspondence? Well, let's try to find the other generators of U13 besides 2. In order to do that, we're going back to Z12 and recall that Z12 besides 1 has generators 5, 7, and 11. And that means U13 besides 2 to the 1 should have generators 2 to the 5, 2 to the 7th, 2 to the 11th. Once again, using our correspondence. Now we can say that 2 to the 5th, 2 to the 7th, and 2 to the 11th are the same as 6, 11, and 7, but I personally prefer these powers of 2 because they really highlight the correspondence between Z12 and U13. Now we'll continue to take advantage of this correspondence between Z12 and U13 to find all the subgroups of these two groups. And the key takeaway here is that Z12 is an additive group, and additive groups are generally easier to work with than multiplicative groups. And so, for instance, here are all the subgroups of Z12, starting from the largest to the smallest. So we have all of Z12, that's a subgroup of Z12, that's generated by the element 1. Here's a subgroup containing all the evens, 0, 2, 4, 6, 8, 12, and that can be generated by 2, by adding 2 to itself many times. We have 0, 3, 6, 9, generated by 3, 0, 4, 8, generated by 4, 0, 6, generated by 6, and the 0 only subgroup generated by 0. So those are the subgroups of Z12. Now, how can we use that to find the subgroups of U13? Well, we use our correspondence. So for instance, which subgroup corresponds to Z12? Well, it's all of U13 generated by 2 to the first. What about the subgroup 0, 2, 4, 6, 8, 12? Well, it's the subgroup containing 2 to the 0, 2 squared, 2 to the 4th, 2 to the 6th, 2 to the 8th, 2 to the 12th, generated by 2 squared, just like this subgroup is generated by 2. Here's another subgroup containing all the powers 0, 3, 6, 9, generated by 2 to the 3rd. And we can see the rest. A subgroup containing 2 to the 0, 2 to the 4th, 2 to the 8th, generated by 2 to the 4th, and the other two once again corresponding to these two subgroups. And so this is a pretty powerful correspondence because once we have all the subgroups of Z12, we can use that to come up with all the subgroups of U13. Now all these elements are written as powers of 2, that's totally fine. If you want to write them as what they actually compute to, well, here they are. For instance, 2 to the 0 is 1, 2 squared is 4, 2 to the 4th mod 13 is 3, 12, 9, and 10. But my personal feeling is that nothing is wrong with powers of 2. We can certainly leave them like this, and we can see the structure of this subgroup much more clearly than if we were to actually compute these powers and write down 1, 4, 3, 12, 9, 10. And so that's a very powerful use of this correspondence to come up with all the subgroups of U13. And here's another thing that I like to highlight. All of these subgroups are themselves cyclic, generated by a single element. And here's a theorem. And for this, please take a look at the chapter 14 reading for the proof. But the theorem states that if G is a cyclic group and H is a subgroup of G, then H is also cyclic. So for instance, we know Z12 is cyclic, and this theorem says that any subgroup of Z12 is cyclic. Same can be said about U13 because U13 itself is cyclic, and all of its subgroups are also cyclic as well. Again, for the proof of this theorem, please take a look at chapter 14 in the textbook. Let's talk about problem 7, where Elizabeth said the multiplicative group bracket 3 behaves just like the additive group Z. What does she mean by that? For now, we'll look at some examples, and we'll formalize this idea when we study isomorphisms a few lessons down the line. But I think the examples we'll look at will be instructive. So in bracket 3, which is a multiplicative group, 3 to the 17th times 3 to the 25th is the same as 3 to the 17 plus 25, which is 3 to the 42nd. law of exponents. The multiplicative identity is 3 to the 0, and the multiplicative inverse of 3 to the 17th is 3 to the negative 17th, because those multiply together to be 1, or 3 to the 0. Now, what's the additive counterpart in Z of all those statements? Well, 17 plus 25 is 42 in Z. The additive identity is 0. The additive inverse of 17 is negative 17. And so addition in Z certainly feels like multiplication in bracket 3. And for now, let's leave it with this example. And we'll formalize this again when we study the notion of isomorphisms a little bit later. But for now, that's the end of this lesson, and I will see you next time.